Great. Okay, please. All right, so no mic. All right. Is there some echo? Yeah, kind of. Okay. All right, start my timer. All right. Hi, everybody. So I should join the rest of the speakers of this week and the past few weeks in thanking the organizers for this nice opportunity. But I've also been given so many tasks that I have a mixed feeling. No, I'm joking. Actually, this has been a great experience so far, and I'm really happy I was given all these tasks. I hope I contributed some amount to the scientific exchanges of this really nice workshop and PhD school. So this particular task was about giving a review of the swampland program, of course, with my own spice or perspective, if you will, which I hope will be more conducive to an audience perhaps who is not familiar with this topic. All right, so I think this picture here more or less summarizes what the swampland program is about. But, about space-time bubbling and doing weird quantum stuff. And before you say, but this is just AI, this was easy. It wasn't. I had to Google for a long time to find this picture. This is not made by an AI, actually. All right. So what is the swampland program about? The swampland is kind of a weird word, right? I mean, it's not particularly self-explanatory, I would say. And the history is kind of weird indeed, much like that little line that appeared there. To me at least, the swampland is about, looking at the big picture, like relaxing for a second and looking at what we know, what the common ground, we start from is, or at least most of us, start from this, which is the gravitational effective field theory framework, right? Which is, the idea is that whatever quantum gravity is, it should look like gravitational EFT at low energies, right? So that's the idea. So in this sense, I had the idea of quoting this Greek myth of the Ariadne's thread and the Minotaur and the labyrinth, in the sense that EFT is sort of the thread that we can start pulling and see where we get, right? Of course, along the way we can we have ideas and we look at the ideas and see where they get us, and if they don't work, we try to understand why they don't work and so on. It's a bit of an exploratory paradigm or approach, if you will. But the important thing I want to emphasize is that it's completely orthogonal to the microscopic things, like, let's think about quantum strings doing stuff, or let's think about non-perturbative renormalization. All that stuff is orthogonal to this swampland approach, which is not about starting from a microscopic theory, but rather starting from what we call the bottom. And I understand that terminology can be backwards with respect to other fields, and see what we can bootstrap from just EFT and similar considerations. Okay, that's more or less the idea. And it's not like we have nothing to start from. Gravity tells us very interesting things, right? In particular, black holes are really cool, right? They have some interesting features that we can start pulling the thread from, namely, their entropy and radiation that they have, at least within the regime of validity of the EFT. And they already hint at some non-trivial features that gravity has compared to other interactions, namely the non-trivial mixing between infrared and infrared physics. And then we can keep pulling the thread by imposing some consistency constraints on the theory, unitarity and so on, like we were talking about in the past couple of weeks. And then, of course, again, it's not like we have nothing. We have samples of theories that we know come from some consistent PV completion, and we can use these to sort of compare with these ideas, right? Like we find some arguments that are based on black hole physics or whatever, and we say, this should work like this, and then we look at the samples, and so far it seems like things match whenever we are confident that they should match. For example, so the point is that not everything goes in EFT. In fact, it's the opposite. Almost nothing goes, right? It's not like you can write down any field content you want. You cannot put like a million different fields or an SO 1,000 gauge group or whatever. You cannot just do that, right? Things become inconsistent for one reason or another. And so one of the goals of the swampland approach is to understand what's wrong with these theories. Why don't they show up, right?
Sorry, are you saying that field theory that you write down is the abstract is they do 1 to the 1,000, it's not an inconsistent theory?
Right, the idea is that the probability that it is inconsistent is 1. It could be that
but
like
inconsistent from what? Maybe it will become clearer, but I just curious about the definition of
very good. Yes. So this is important. So it can be perfectly consistent as a non-gravitational QFT. Exactly. So the point of the swampland is not to identify stuff we already knew, right? For example, gauge theories with gauge anomalies are inconsistent on purely QFT grounds. Swampland constraints are about identifying inconsistencies that are purely related to gravity, not just field theory constraints without gravity. That's the idea. So this is more or less the picture I was trying to convey, and I'm kind of proud of this. I made it myself. So you see, like whatever UV completion, perhaps plural, perhaps singular, I don't know, and I don't care at this stage. We have here. The point is that what we see is more or less that very few, low energy sectors seem to show up. That's more or less the picture. And the idea is that this red area of like QFTs that look okay but are gravitationally inconsistent is the swampland, right? The place you don't want to go, right? That's where the name comes from. All right. So this is all fun and games, but why should we even care in the first place, right? We have good reasons to believe that at least one EFT is okay, right? The standard model. So why should we care? And the reason, at least some reasons, in my opinion, is that first of all, why things can be consistent or not gives us, insights from a purely theoretical standpoint on what quantum gravity should look like. But it can also be interesting for phenomenological applications. Although I'm not gonna focus much on these because it's a review. The idea is that because not everything goes, in fact, almost nothing goes, there can be consequences for low energy physics. So it's not necessarily the case that quantum gravity in physics is relegated to super high energy scales. Right? It could be that there are some consequences. And we have ideas about some of these consequences I'm going to talk about. Turns out the standard model checks the boxes so far, which is on one hand good because it's consistent, but also on the other hand it's kind of sad because we could have hoped for things of new physics at that stage. But alas, that's it. But still, I think it's worthwhile studying this approach. All right, so usually when someone presents this topic, puts up a picture of this height, which I'm not particularly a fan of, because it's kind of I feel like it's a bit confusing. It's like, here's this huge network of ideas, and like I'm not going to explain all of them, but look, trust me, they're well motivated or partially well motivated and connected in all these different ways. To me, this is very confusing because it doesn't really go to the heart of the issue, in my opinion. Like it feels like people are just proposing ideas willy-nilly, but it's not actually the case, right? This is why in this talk, first of all, I'm going to focus on only some of these ideas. And most importantly, I'm going to try to convey the motivations behind them because I can make up whatever idea I want, but it doesn't matter. The important part is whether I have good reasons to consider this idea. to me, that's really the important part. And furthermore, I will try to convey some logical connections between these ideas that sort of reinforce more or less the story that people are working on, right? So instead of giving like this huge network of ideas, I'm going to just divide the talk in two parts, but it's not 50-50, it's more like 70-30. So the first is just purely about kinematics, meaning no fluid equations, no actions, and therefore no approximations of that kind, right? No truncations, no stuff like that. I only talk about kinematic features like charges, symmetries, stuff that is supposedly robust, right, against approximations. And this is why it's the bigger part of the talk, because in my opinion, it's the sort of more solid foundation to everything else. But on the other hand, kinematics can only tell you so much, right? One thing that it can tell us is like, magnetic monopoles should exist. Great, but at which mass? That approach doesn't tell you that, because masses are dynamical quantities. And that's why in part 2, I'm gonna, talk about a bit of the dynamical aspects of, what we can bootstrap from EFT consistency with gravity by basic consistency requirements. And one thing I'm going to have to leverage to get some mileage out of this is some weak coupling limit, in which we can say some more at the price of focusing on one particular limit. And just to mention, this limit in particular will exclude everything that was said in the previous seminar, because it's a limit in which like some parameter is taken to 0. So it's not it's sort of complementary to what was said in the previous part. And here you can find some review material at the bottom. There's also some more stuff, but feel free to ask me later, of course. All right. So this is part 1. And so this is more or less my version of the picture I presented before. And you're not supposed to understand what this means now, but hopefully you will understand some of it at the end of this part. Also, I'm writing a paper about this with some of the organizers, so hopefully soon you will see a more fleshed out explanation of some of these things. But some of these ideas really need some heavy duty algebraic topology machinery. So, bring your donuts and mugs for this journey. All right, so where do we start? Well, we start where I mentioned black holes, right? Black holes, in my opinion, are one of the most interesting hints of quantum gravity from EFT. In particular, the features that we care about that give us these hints are features that are quantum gravitational in nature, and yet they are reliable in the EFT regime. So something we can trust, reasonably trust. And the one thing that gives us these hints is the Bekenstein-Hamilton entropy as a leading order term, as a leading order area law in the limit in which these black holes are huge, right? This is a really insightful relation because it contains a lot of interesting things. But more importantly for us, at least to begin with, is that it means that black holes have microstates. They are mixed states with some microstates, and there are a lot of these microstates, right? So if you look at the density of states of high energy black holes, it scales super exponentially in the energy, which means that somehow large black holes, which are sort of tame infrared objects, know about the very high energy spectrum in a way that vastly overtakes any other type of spectrum, like any field theory spectrum. In fact, this kind of super exponential spectrum is so-called non-localizable. It cannot be described by local fields, even if non-locally interacting. Right? So this is a deeply characteristic thing about black holes, in my opinion. And we can sort of try to leverage some hints about quantum gravity from this. And then, of course, we have the radiation, which will play sort of a minor but non-vanishing role in this idea. So, okay. So, was there a question?
No, I think you're coming through.
All right. So great. Black holes are super nice. What can we learn from them, right? So one thing we can start learning from black holes is one of the basic things about kinematics, symmetry, right? So let's think about a theory of gravity with some global symmetry, and let's think about black holes. I mean, it's not like we can ignore black holes. Black holes are there. So let's make a huge black hole, and let's throw a bunch of global charge inside. I'm sure you've heard some variant of this argument, but some variants are more precise and careful than others. So let's say you throw a bunch of global charge. What happens from the outside? What happens is that as long as the black hole is large, the dominant contribution to the radiation is statistically blind to the charge. So on average, you will radiate zero charge. Or at least there's a non-vanishing probability, that's my point, that it will not radiate any charge insofar as it becomes big. And the corrections to this are sublinear in one of the mass, let's say. And what happens is that if you let it evaporate just a little bit, just to the extent that it gets to the mass it was before, then it looks the same as the preceding black hole, with the exception that we throw inside an arbitrarily huge amount of charge, at least if the symmetry is continuous, we can do that. And so what gives? It seems like we have violated the Beck-Einstein bound, because now the entropy is infinite. It's not just bounded by the area. So the conclusion here, with some loopholes perhaps, is that in fact we were wrong in the original assumption that the symmetry was, symmetry. In fact, it should be broken by something. So actually, this argument, or some variant of it, was discussed way back in the 50s. So you could say maybe the swampland approach started in the 50s, if you're really bold about it. But lately, people have actually understood more in detail that in fact these symmetries are expected to be broken, because of course you can have field theory effects that irrelevant operators are breaking, but at least some gravitational instanton effects should come in and break this. And we will see a bit more about it soon. And so we can actually sort of give bounds, very weak but non-zero bounds on these breaking effects. But of course, there is at least one loophole that you can think of, and it's like, oh, but wait, maybe the charge gets radiated after when the quantum is so big. But you can also circumvent this loophole by engineering a situation in which the black hole will not be able to radiate away the charge, whatever you compute in it, right? You can make a situation in which, to use a word that I read in this literature, gets constipated. Right? The black hole is kinematically unable to shed the charge because it gets to a situation where you stuffed so much charge inside and you waited to get, with a non-zero chance, a situation in which the final mass is still huge and therefore reliable, but not huge enough to radiate away the lightest charged particles that we have in the field. Right? So what happens is that these would be huge remnants that create a bunch of issues that were discussed in the literature. Again, in the reliable regime, it's not like we're in the microscopic regime where everything can happen as far as we know. So it still seems like we're violating some bounds within the regime of validity of the theory, unless symmetries are broken. Right? And again, we will see another way to arrive at the same result completely independently, which sort of supports this idea, even though here I'm just sketching. So this is one thing we can learn from black holes. But what about gauge redundancies. I don't like calling them gauge symmetries because they're not really symmetries. But what about a gauge theory? So if I have a gauge theory, for example, Maxwell theory coupled to gravity, what happens is that I can make charged black holes. But now the charge is physical in the sense that charged black holes are different from uncharged black holes, and I can measure the charge at infinity with the flux of the electric field. And this is a really basic thing, but also kind of deep in the sense that it gives us a fundamental operational way of distinguishing the global symmetry from gauge redundancy. You can measure the charge at infinity versus you can't, right? And in fact, this is also something that resonates with the idea of holography in gravity, right? In the sense that it makes sense that the gauge redundancies are available in gravity because holographically you can define and measure the charges, whereas a global charge you cannot even define holographically. There's absolutely no way to encode the data of a global symmetry holographically, right? So this is also a way to understand why global symmetry should be absent. So here, for gauge redundancy, the above argument, this doesn't apply, of course, but something else does apply. So there's still an entropy. There are still microstates, and these microstates are charged, right? So we should be able to conclude that in the UV completion, again, kinematically, so whatever masses they are, there should be states with any charge that is allowed for a black hole. Is this any possible charge? Well, if you're brave, you can say, sure, any possible charge. Or you could say, no, wait a second. I mean, black holes are microscopic objects. They should only have microscopic amounts of charges or zero. But still, charges are not just any structure. I mean, they form a lattice. You should be able to add, subtract charges and so on. So I can make microstates with charges Q plus 1 and Q, which are big. And therefore, by the lattice structure, the unit part should exist in the spectrum. So this idea tells us that the spectrum of charges in a gauge theory coupled to gravity should have all possible charges, namely all possible irreducible representations should appear in the space of states. Right? This is called completeness. The spectrum of gauge charges should be complete. That's it.
If you're using microscopic or infrared buzzing,
Yes,
compute something about.
that's
But
right.
I guess that's the whole
point.
framework. But you don't expect anything new then in terms of the ultraviolet. You don't expect anything new at scales that we really are in the deep quantum regime. You still expect this construction to hold those scales.
No, that's not what I'm saying. So
I mean,
the point is that this argument tells us that states of all possible charges should exist. This is some information about the full theory, right? Regardless of whether the infrared theory already has them. So, for example, I mean, it's the output of this argument.
I mean, yeah, those are the assumptions you want to put into what you call a consistent theory.
The assumption is that the UV complete theory reduces to EFT in the appropriate regime, in the low energy, long distance, whatever regime. And then, because this argument takes place within this regime of validity, in fact, asymptotically so, like I make this black hole arbitrarily big, so I can make it as close as I want to, as reliable as I want. That's the point. It's a parametrically reliable regime. Okay, so great. So let's take a quick stock of what we saw. So this is, swampland 101, more or less, like leveraging bottom-up infrared ideas to learn about quantum gravity. So we learned, okay, we have at least some suspicion that the global symmetry will be broken. And we have, more concrete calculations recently with, gravitational instantons that seem to support this idea. And completeness, namely this idea of the spectrum of gauge charges should contain all states. So these are, a couple of interesting things, but again, this is kinematics. So these states may be there, but they could be as heavy as the Kazakh scale or even more. So, for example, we could say like, oh, because I can make magnetic or ionic black holes, monopoles should be there, okay, right? But they could be super heavy. So can we do better? So the answer is yes, but not in the way that you may like. So we can do better in the sense of we can sort of rederive and generalize and sharpen these ideas from a different angle. And this is where the donuts and mugs come in, because I'm going to talk about topology, in particular, topology fluctuations of space-time. Right? And there are, again, some caveats that are addressed by working at this kinematic level. So we're not actually writing a QFT path integral and summing over topologies. That doesn't work, right? For many reasons. The point is that we don't need to do that, right? These, in EFT1 usually just sums over few subtle points that contribute to semi-classical limit. And even that we don't need to do because we're working kinematically at this level. Right? So why should we even consider topology outside of the, some idea of like, it's a natural thing to do, right? Well, it is in fact a natural thing to do in the sense that all other interactions do the same, right? In each theory, we sum over the topologies of the principal bundles that define the kinematic structure. And we have to do that. We cannot just not do it because otherwise we lose some key properties of quantum theory, like cluster decomposition, for example. You cannot not do that. Now, in gravity, the story is a bit more subtle, but you can still analyze what happens with gravitational instantons analogously with gauge theory. And in fact, some first words about this were written by Whitman in the 80s. And they involve certain kinds of instantons like exotic spheres and things like that. Yes?
Previous slide is for no summing of
That's no. What I meant was you cannot do it directly with some QFT path integral. That doesn't work. But we don't need to do that. So whatever the UV, you cannot enumerate, topologies in dimensions higher than at least 3. So you cannot just index them and sum over them just like that. It doesn't work.
You mean to say that the sum will decide?
Yes.
Is that what you mean?
Yes.
You could in principle do it if somebody said, here are the full relation. You don't know how to
I think it cannot be done. But okay, I think it's a result that at least in some dimensions, like in 4D, you just can't do it. Okay? But anyway, yes. So another motivation, it comes from this nice conceptual paper about what true background independence means in the sense of lack of fixing any possible structure, including space-time topology. Of course, up to perhaps asymptotic boundaries we may not want to fix in some super selecting settings. But another reason is that, more practically, it just works in the sense that it produces black hole thermodynamics in at least 2 independent ways using summing or sum over topologies like wormhole or gravitational instantons. And it produces the results we already knew from other calculations that don't. So the fact that they match is at least some hints that, we got to include some non-perturbative effects in gravity, and in the semi-classical limits, these instantons involve some topology change. We shouldn't just ignore the business time. And finally, the sum over topologies is actually required from holography. So if you want your theory to be holographic, and in my opinion, there are good reasons for that. Basically, it comes from the fact that the quantum theory in the holographic description is a quantum theory. So you can do superposition of states and entangled states, and in the bulk description, these are, in fact, topologically non-trivial wormholes and similar configurations. So how to describe topology change kinematically? So again, we're not like writing some sum over them, but at least we should try to classify them. And some classification can start by asking what is the basic thing I can do to space-time topology? And the answer is I can just make a teensy tiny little wormhole. I can, create like a building block of topology, so to speak. And then if you ask, how far do you get by doing all these possible operations called surgeries? And the answer is that you cover an equivalence class of your stacking manifold up to cobordism equivalence, right? So what is cobordism? Well, so cobordism is an equivalence relation between manifolds with some pre-assigned structure. So for instance, we may want some spin manifolds, or we may want them to carry some principal bundles that are gauge groups, or whatever structure the physics wants. Up to this structure, we can basically think of like taking one manifold, doing all possible surgeries to get some other manifold, and this defines an equivalence relation. There is the actual definition is that this joint union is the boundary of a higher dimensional manifold with the same structure with appropriate conditions.
Are these cobordisms all in the hidden section?
So there are at least 3 different answers to that question. So one is yes. The other answer is this is kinematic, so you don't need to worry about that because you don't need to care about like whether.
Because the cobordism classes depend on the signatures of the.
Only if you care about the metric. So these are topological manifolds.
Even if it's topological, right? If you want to construct a Lorentzian structure,
That's
any Lorentzian.
That's right, but that's the point. So
things are not subordinate to each other if there is a Lorentzian structure.
if you put that structure on top, which here we're not doing, but either way, so answer number 2.
The answer is that it would not then support a Lorentzian.
If you don't do it in the Euclidean, yes, you can do. You can do it in the Euclidean if you want. You can just say, oh, I'm not putting the structure yet. Or third answer, you can do it, but you can do it because you see these relations defined for compact for closed manifolds. So you can define this relation in terms of what are called gravitational solitons. So you can take your Lorentzian manifold, you look at some local slicing, for the global in general, you can't. And then you attach you close the soliton, you close the manifold with whatever topology, you attach it with a connected sum construction. And you can ask about summing over all possible such solitons, which avoids this issue. So there are at least 3 different ways of addressing this point, but it is in fact a good point. Great. So great. So we have a mathematical formalism for asking questions about topology chains, at least kinematically. And then what can we learn? Well, we just said that summing over topologies, at least kinematically, just moves you inside a cobordism class, right? And you can have multiple classes that will not talk to each other. So if you sum over topologies in the sense of summing over surgeries, eventually you will sum over surgeries in some class and summing over the classes. Now, again, from this holographic point of view, if this sum were non-trivial, if you had more than one class, so in other words, if the sum over topologies is not trivial, like if you have some obstructions, you cannot reach some topologies starting from other topologies, then the holographic description would break, in the sense that you wouldn't have a bona fide Hilbert space. You couldn't just do any superposition of states you want. You cannot entangle and disentangle, separated states and so on. The dynamics wouldn't be local, all sorts of issues. And there is a ton of literature on, what kind of issues you will get. But there is a simple fix. The simple fix is to ask that no such obstructions exist, right? So the group of cobordism classes should be trivial. There should be only one class. And this is called cobordism triviality. And
that's what you're imposing.
Yes.
That we only look at one, you choose one cobordism class and decide that that's your theory.
No. What we're imposing is that a UV-complete theory should have a tangential structure such that the corresponding group has only one class. This is a condition on the UV-complete, at least in some regime where space-time makes sense, of course. Otherwise, you got to generalize what you mean by coordinate. So this is a a rich topic that I don't really have a lot of time to explain. But it's a condition that at this level we are motivating from holography. We are motivating from fixing a bunch of pathologies from holography, and this actually buys us something. So if we impose this condition, turns out this condition, this reality condition, and I can basically move to any topology I want from any other. Turns out it's equivalent to the absence of global symmetries. Right? So something we motivated from black holes, turns out it's equivalent to this thing that we motivated from summing over topologies. Pretty neat. So how does that work? Well, one thing is that, one arrow is that you can consider certain configuration of space-time where we have like a gravitational soliton. You can build it from a non-trivial cobordism class representative. We have some connected, some construction. In pictures, you just stick a little blob of topology on your manifold, at least on a local slicing. And the idea is that it must be able to match, that there must, at least kinematically, there should be such a configuration. And what does this mean? Well, let's say it wasn't able to do that. Well, then this equivalence class, this cobordism equivalence class represented by the soliton would be a conserved charge, right? If it's a non-trivial, because again, topology change cannot just change the class, cannot get outside of the class. It means that this thing is a global charge. It's conserved.
Sorry, what do you mean by this?
It's a metaphor for that this class is trivial, that there is a cobordism between this and this.
But these are all on the same space, or I don't not understand. This is like a maybe a
Sure. But it's an abstract process. You can imagine like doing a cobordism in which like every snapshot of your process is a slice in this picture.
But your theory, like your space-time, physical space-time is on the bound.
The asymptotic boundary is fixed. Yeah. I'm doing this thing locally. I'm doing some local pushy slicing, and I'm sticking a soliton on top.
So when you say soliton, you mean a prime manifold or something like that. So some
In a closed manifold.
I'm saying a prime manifold, like a connected sum with some prime manifold.
Yes, with a representative of a non-trivial class. I can give you some examples here. But the point is that, you see, if this class were non-trivial, this would be a conserved charge. I wouldn't be able to do this. And so if I require that no global charges exist, then I must be able to do this. Well, there is a reverse argument, and I'm sort of running out of time because of lots of questions, that in fact, by asking this, you actually do break full symmetries. And you may wonder, but this is weird because cobordism charges are abelian, but in general, they can have non-abelian symmetries. It turns out that there are some particular solitons of that type that do break the non-abelian piece, the commutative subgroup. And all that's left is abelian charges that can be broken by asking that that Bordism groups to be trivial. So bottom line, these things are equivalent, non-trivially. And furthermore, this triviality also implies the other thing we said, starting from black holes, and completeness. And you can think of it as, what does it mean for the spectrum of gauge charges to be complete? So for example, it means that in Maxwell theory, electrons exist, particles with charge 1 or -1, not charge multiples of 7. And the reason is that another way of saying this is that, in gauge theory, you have some extended line operators here, Wilson lines, Toft lines. And if you have a complete spectrum, you can stick a Wilson line on some charged particle to end it on a particle, or any Wilson line, right? Not just the ones with charges multiple of 7. So completeness is equivalent to being able to end all of these operators with some caveats that are explained in the literature. Bottom line, the probability of reality is equivalent to being able to do this with any extended operator. And also it's also non-trivial equivalent to, again, asking that a certain symmetry be broken. So you see, all these ideas are interconnected. This is what I wanted to say. So, you know, we start from black holes, we get somewhere. We start from topology fluctuations, we get to the same thing with very non-trivial, you know, proofs in between that these things are equivalent. So it's really remarkable, in my opinion, that these stories reinforce each other. And finally, another thing we can say from the kinematic point of view is that the presence of these topology fluctuations induce new anomalies that you must worry about in order for your theory to be consistent. It's not just the standard gravitational, perhaps, or gauge anomalies that were familiar from the 80s. There are some new anomalies that appear when, you know, you look at some closed path in field space, in the space of gauge fields or gravitational fields, to see if your observables are gauge invariant, right? And the point is that if you include topology fluctuations inside of this path, then you run into new anomalies, right? These are called Difrid anomalies, and they have been shown to constrain some theories non-trivially. Like there are some genuinely new constraints that were not there before. And the standard model survives these constraints non-trivially. Like it could have been that there were new anomalies, but there aren't. Whereas some theories are killed by this. They would have been consistent otherwise, but they're not if we do this. And again, this matches with the samples that we can collect from like top-down constructions. It's a completely independent check of consistency. So this is sort of a picture of what I mean. Like you can construct like a path in field space-time by doing what's called a mapping towards construction. I'm not going to explain the details because I don't have time for it. But what changes is that, you know, once you have topology fluctuations in the game, types of manifolds that you must consider to evaluate your anomalies on are more, you know, they're richer, and so you can have more constraints. Good. So I hope that now this picture makes a teensy tiny bit more sense to you. Like it's sort of logical relations I explained between the probabilities of reality, holography, you know, and the basic constraints that we derive. So the absence of global symmetries and the completeness of charges, and the key role that black hole entropy plays in this. Good. So now let's switch to dynamics, right? And dynamics means, you know, evaporative radiation or S-matrix for another fragment.
I think it is. Because the key role that black hole play, but we also said that there are all these other alternative arguments.
Yes.
Can you, if I'm suspicious about the black hole argument, that it's survive?
I would say so. If you start from like holography, yeah, I would say that. In fact, in the paper we're writing, we're doing the opposite. We're saying like, suppose you don't trust the second one, then this. Yeah, right. Okay, so let's look at dynamics really fast. So what can we say? Well, we can look at the other thing that black holes give us, radiation, and then similarly to you know the preceding part, we can look at something a bit more solid, like S-matrix consistency conditions, for example. But in that case, we sort of must take some weakly coupled limits to say something more concrete. I will explain what that means. But the upshot is that the radiation of black holes suggests that in some sense gravity is the weakest force when other forces are present. There is a technical meaning of this so-called Weak-Wright conjecture. And the second thing is that at least when the UV completion is weakly coupled, parametrically, so again, it doesn't concern what you said in the previous seminar. Somehow it looks like consistency of scattering amplitudes and gravitons tell us that something strange must happen. I will say a bit more. So let's start from, again, the radiation. So again, another, you know, sort of half-heuristic Gedanken experiment. What happens if we take a charged black hole in some electromagnetic field, and but with this time with a lot of charge, and we'll just let it evaporate, right? What happens? So either it reaches the extremality bound and then it stops, That's great, but this is kind of a fine-tuning scenario, both in parameter and probability. So we can just avoid it. There are other scenarios which can happen. The second scenario is that it approaches extremality, and this goes like autocorrect, it should be extremality. And then if it decays more, it will generate a naked singularity in the regime of validity of the EFT, which is kind of weird. Again, this is so far the best thing that people have been able to come up with, to my knowledge, without assuming anything else. Not great, but at least it's a hint, right? That something was wrong if we can just approach extremality without any problem. And this scenario, the last scenario is that it can just keep decaying without approaching extremality. In fact, getting farther away from extremality, closer to Schwarzschild, right? But to do this, it must be able to radiate more charge than mass, right? To shed the charge faster than mass. This means that there must exist at least one state whose mass is smaller than charge in Planck units with some precise coefficient. And this is the requirement that's called, the weak gravity condition. And the conjecture is that this condition is true. So in particular, you see the scenario number 2 is problematic because this would lead to some sort of constipated remnants that are not protected by anything. They're not extremal. They just should be able to decay, but they don't, and they create like a bunch of pathologies in the spectrum because they're not just extremal, but you have like a range of these black holes, and they should all contribute to amplitude. It's a mess. Now, again, this is again a partially heuristic thing to say, but at least it hints at the idea that there should be sufficiently light particles, which in the standard model is true, in fact, by a large margin. The electrons, for example. And it seems to be true also in all samples of theories that you can think of from the top down. And in some classes of cases, you can actually prove that it equilibrates in perturbative theory or stuff like that. So this is a non-trivial thing that this heuristic argument agrees with some actual proof that you can discover. Another neat thing you can do with this argument is that you can apply it to magnetic trends, which are coupled to the inverse coupling, right? Just from EFT considerations. And you can discover that because in the EFT, the masses of monopoles are bound by a certain, like the cutoff over G squared, the solitons. If you do some algebra, you discover that the cutoff should be bounded by, not by the Planck mass, but by the H coupling times the Planck mass, which can be parametrically different in a weakly coupled theory. So again, this is a non-trivial UV-IR mixing kind of relation. And people are studying it in top-down examples and trying to prove it and so on. But at least the heuristic argument is there. I think we should at least look at it. Good. So can we do something a bit sharper, as in this case with topology fluctuations? We were fairly sharp about the conclusions. Can we say something more? In my opinion, yes, but in some weakly coupled limit. The weakly coupled limit in gravity means that UV cutoff of the gravitational sector of the EFT. So not the field theory part, which can come from integrating out some massive particles. Actually, the gravitational that contains curvature corrections weighed by some Planck scale contribution. This cutoff should be small. And the reason is that if you scatter gravitons, you see that at low energies they're weakly coupled because the couplings are derivatives. That's just EFT consequences. But if you want the UV completion to be weakly coupled, whatever lies beyond should also satisfy this. And therefore, this condition should be valid parametrically. So if this is true, if the UV completion is weakly coupled, we can say a lot more sharply, right? More sharply. And again, why bother with this case? A good reason is that it's easy. We can say more. But also because we have examples, right? In weakly coupled strings, for example, we can actually provide at least toy models where this is true, and we can compare. But another reason, which is also suggestive for me, is that it's optimistic for real-world physics in the sense that if this is true, new physics appears soon. Like it's not just Planckian everywhere. So we can hope to say something that our experimentalist friends could test. Maybe not in 5,000 years, maybe in 500. But anyway, it really depends on technology. But still. And finally, I just gave you a bound from before that may hint that, weakly coupled theories in other sectors could also become weakly coupled gravitationally. And there are other arguments that I don't have time to get into, that perhaps you must need this regime to make the EFT work, but it's not completely clear yet. So let's say we do consider this, then a UV completion must occur at 3 levels because of how the structure of couplings play with the diff invariants, right? They must reconstruct the diff invariant diaphragm. And so you can show that the completion must occur at 3 levels. So, scattering amplitudes, for example, must behave in a certain way. They must be written in terms of, virtual resonances with simple poles and logomorphic amplitudes and so on, because we're doing perturbation theory in a reliable regime. And so we can apply some neat bootstrap techniques. We can sort of make an ansatz for, this is a fairly general, or even the most general amplitude that has the correct structure that reduces to GR at low energies. And, is unitary, is causal, and all of that stuff. And if you do that, you discover that, whatever lies in here, whatever the spectrum of weakly coupled states that we will be completion, cannot be whatever you want, right? This is the spirit of this problem. It seems like it should be made of higher spin degrees of freedom, which form an infinite power. And furthermore, the actual amplitudes and the actual masses of these guys are constrained. Like people have not been able to obtain amplitudes that are basically not qualitatively different from the ones that appear in string theory. Again, this is all in weakly coupled quantum data. But still, there's a huge amount of literature evidence. Okay, so what else? Let's say we start here. We're doing weakly coupled quantum gravity. We have this idea that the spectrum should include these infinite towers of species. Can we constrain them from something else, not just as matrix conditions? Turns out we can, and we can again keep pulling the thread of consistency with black holes. And there's this neat picture that because the minimal black hole I can make knows about the UV couple, which can be much smaller than Planck, these towers should have somehow appear in the thermodynamics of these black holes. And this was made more concrete in some recent papers by, for instance, people in my group in Munich or in Harvard. And essentially the idea that the consequence of this correspondence between these new physics, degrees of freedom, and smallest black holes I can make, is that the thermodynamics of these two pictures should match. And this is a non-trivial condition, right? It could be that they don't match. What happens is that if we compare the thermodynamics of these towers to the ones of the minimal black holes I can make, again, by pulling this thread, this is me in this picture. So, although it really does resemble my path, by the way. So if we keep pulling the thread, we find non-trivial consistency condition for the density of states of these new degrees of freedom. And we find that they sort of quark-like, they have the same density of states as two options. Either, Kaluza-Klein states, which just means that, we have extra dimensions and we sort of move the problem to the higher dimensional theory. So it doesn't really solve the problem, it just moves the problem. Or we have some sort of exponentially scaling density of states up to some reparameterizations, which were classified partially in this table from my paper with the Munich group. And other kinds of spectra just fail to do this, to match with the minimal black holes. So again, there are no trivial consistency conditions that you can just, at least try to bootstrap from infrared physics in this way, in this limit. So yeah, this is pretty much what I wanted to say. Now, there are way more detailed and super technical papers that really delve deeper into this business, both from the kinematic side, anomalies, cobordisms, and so on, and from the dynamical side. And there are some interesting results when you couple all these strategies with some heavy-duty simplifying machinery like supersymmetry or higher dimensions. And the result is that, for instance, in high dimensional sphericality, you really can nail it down. Like you can classify EFTs and you can say, ah, this is good, this is good, this is bad, this is bad, this is bad. And then you can compare with the samples or examples that we can classify from the string landscape, let's say, and they match, right? They always match whenever we can answer whether they match. And it's a non-trivial thing because they could have just not matched. It's not like we're changing things around. There's no freedom. And so it seems like really these ideas that sometimes have more like heuristic flavor, they seem to have some substance. This is my message here. And sometimes we can actually, the idea is that in a given microscopic framework, you can maybe aim to prove some of these things. And in some cases, this has been done. In the CFT for perturbative string theory, some of these things, some of these statements are actually proven. And then on the pheno side of things, again, I said that even the most widely speculative claims in this business seem to be valid for the standard model. So it's not like there's much hint for new physics there. But if people have been trying to come up with some scenarios where these conditions constrain new physics, especially about axioms or susciperating if there is any for cosmology. So there's some literature there on the more pheno side, but also on the more speculative side of things. And I wanted to convey that there is a more solid foundation to these ideas, and then people just go on more explanatory paths. And the basic message of the swampland is that if you just look at EFT naively, you may run into issues. So beware of the swampland. Thank you.
So we are super late. There is one very short question. Otherwise, we go for coffee break and we ask more specific question to Ivano afterwards.
Or during the coffee.
Or during the coffee break. Okay, then let's go for a coffee break. Thanks again, Ivano.